Now, to understand how and whether such a planar object might actually be able to propagate through space, we of course have to use the physical laws which describe how fields behave. And these, of course, as we know, are Maxwell's equations. So to review those, I have written them down for you again here, as we've reviewed several times now already. But we are particularly interested now in empty space. So we're going to make a few modifications to remind ourselves of that fact. Now, in empty space, of course, there are no charges. And because there are no charges, we don't have to worry about the Lorentz force law. We don't have to worry about forces on any charges because there are no charges. In addition, several of these equations actually simplify for us. If there are no charges, if we are in empty space, then we know the charge density here is exactly equal to 0. So the divergence of the electric field for us is going to be 0 because we are in empty space. Also, if there are no charges to move around, there are, of course, then no currents involved, and so the current vanishes here as well. So these are our basic Maxwell equations, and we have to make sure that this pulse that we're trying to describe is consistent with these equations. So in particular, let's take a look at our first equation. This seems to be the simplest, that the divergence of the electric field has to be 0. And let's see what the implications then are going to be on our electric field. So if the divergence of the electric field is 0, I have to have 0 is the divergence of my electric field. And that tells me then that the derivative of the x component of this electric field with respect to x plus the derivative of the y component of the field with respect to y plus the derivative of the z component with respect to z have to be 0. Now, the beautiful thing about having a planar electromagnetic field like this is that it depends only on x and t. Everything is constant as I vary y or if I vary z. That being the case, this derivative here, all derivatives with respect to y have to be 0 because things are constant with respect to y. Or if you look at my electric field, it doesn't depend on y, so its partial derivative with respect to y would give 0. Similarly for the partial derivative with respect to z. The only thing that isn't 0 is the derivative here with respect to x. Now, this is a very interesting result. The x component of the electric field we see has no derivative with respect to x. Its derivative is 0. That implies then that the x component of my electric field has to be constant with respect to x. Now that's a very powerful statement if we think about that. What that means, constant with respect to x, really means completely constant. That means whatever value it has, say at this particular location, is the same value it's going to have for any value of x, anywhere in here near the origin or over here to the right, or in fact anywhere off to positive infinity or off to negative infinity. It is exactly constant. So then I can tell you then that Ex with respect to x is constant. And because it's constant in particular, it also equals its value when I am out at infinite distances when x equals infinity. And if we think about any experiment that we might actually be trying to carry out, such as here I'm showing the experiment that we had looked at previously when we considered conservation of energy, right? You can imagine, okay, I could set up all kinds of interesting electromagnetic fields here in my laboratory where I have my apparatus, but they are never going to result in any electric or magnetic fields off at literally infinite distance. So I know at infinite distance, the x component of my electric field actually has to have value 0. But because this thing is completely constant with respect to x, for all of space, I know that the x component of E equals 0 for all locations. So the electric field then can have no component along the x direction. And if we're imagining that this thing is going to depend on x and time, so it might be moving along x, we see immediately that its x component has to be 0, tells us the field has to be perpendicular to x, or more generally, if we were moving in some other direction, and we're always going to agree for this analysis to set x equal to the direction of motion, what this tells us then is that the electric field always has to be perpendicular to any direction of propagation of such a pulse. And that then leaves us to our second choice of coordinates. Since the electric field has to be always perpendicular to x, what I'm going to do is I'm going to take whatever direction that it points in, which is perpendicular to x, and I'm going to define that as the y direction for my coordinate system. Right? I have the freedom to choose my coordinate system at will. So what I'm doing now is I'm saying that this electric field, which in general depends upon any location, x, y, and z, or I can gather them into a vector r in time t, is going to have this very specific form that it is going to be some function, right, of x and t only. It's not going to depend on y or z, as we've already said. But now I'm just writing a scalar function because I know that I can always choose the direction of my y coordinate to be the same as the direction of the electric field, the one that is perpendicular to my direction of propagation. Now, since the y direction in vector notation is the j hat direction, I can then reduce my problem from this one assumption I've made of a plane pulse. Immediately, I have the implication that the electric field has this very particular form as some function of x and t times the j hat direction. Now, that's very useful. Now, given that, we can begin to think about the structure of this function f of x and t. So let's begin to consider those features as well. So here's a sketch of f of x and t that describes the magnitude of my planar electromagnetic pulse. So this is going to be position x along this coordinate. This axis gives me the value of f. And I want to consider the possibility that this clump of electromagnetic energy, described by any shape, some function f, we don't know anything about it yet. This is the most general planar electromagnetic or electric field I can set up. And I want to consider the possibility that the energy stored in the electric field here can move through space. So I want to consider the possibility that as time changes, this shape is going to be moving forward. So if I take, for instance, some generic shape, some function f of x, and I want it to move forward, say, by some distance a, if I make that happen, right, and I'm going to draw my function as it's moved over, like so, mathematically we know how to describe that. We would say that this shifted over version of my function is just my original function f of x minus a. Because when we shift functions rigidly, if we want to shift them forward, we subtract a. The reason for this is as follows, right? If we consider some point on my function, say this little piece on the original function, which is where I get the value f of 0, and I consider where that point ends up, after I've shifted the whole function over by a, that point's going to be over here somewhere now, right? And you'll notice if I take this dashed function as f of x minus a, and I substitute in a for x, I'll be evaluating f of 0, which then tells me that this point here, indeed, after the shift of a, corresponds precisely to the original point here on the left. So this is the standard way of shifting a function forward. Now, I want this thing, though, this pulse of mine, not to just be shifted over. I want it to be shifting over as time evolves. So what I would really like to do is to say that the distance that I've moved, this distance a, is equal to some velocity v times time t. So what I'm going to suggest that we consider then is that f, the function that describes the electromagnetic field at any location in time t, is going to be this shifted over version of this shape function f, and that shifted over version depends upon time in a very specific way, namely the amount of my shift a is equal to just v, some velocity v, times the time t. So, putting this all together, my new form that I have for my general electric field at any location and time t, when I've chosen this planar case, tells me that it's just some function times j hat. But now that it's a pulse, in other words, something that is moving, keeping its shape and just moving rigidly in time t, the dependence of this function has to be as position x minus the velocity of my pulse times the time t. Very good. So now we have used up our first Maxwell's equation, and we're certain now that we have satisfied that one. The next thing we should try to do is to bring in the next Maxwell equation. So since we've been working with the electric field, we've already used up equation 1. Let's now work on equation 3. And let's keep track of the equations as we use them. So here is where I used Maxwell's equation number 1. And now I'm about to use Maxwell equation number 3. I'm going to calculate the curl of this electric field. And then I know that that is going to tell me the minus of the time derivative of the magnetic field. So let's work on calculating the curl of my field. Now curls, as you know, we calculate very similarly to how we calculate cross products. We form our determinant. Along the top row, we put I hat, j hat, and k hat. Along the second row, we put our gradient operator, or d by dx, d by dy, and d by dz. And on the final row, we put the electric field, Ex, Ey, and Ez. Now, of course, a lot of these things we already know are zero. We've already determined, for instance, that the x component of the electric field has to be 0. And moreover, we defined our coordinate system so that the z component of the electric field is 0. We define things so that only the y component of the electric field is not 0. So let's reflect that in our calculation. So we have I hat, j hat, and k hat. Derivatives with respect to x, y, and z. And the electric field has, in fact, no x component. Its y component had this very special form. It was f of x minus vt. And our electric field pointed along y. It had no z component. So this here is 0. So now we need to calculate this determinant. And so we can go ahead and carry through on our calculation. You guys, I believe, know how to do this, right? You do the cofactor expansion across the top row, for instance. So we would have plus I hat times. And then you imagine crossing this row of the matrix out, and you do this littler determinant. Partial y derivative of 0 is, of course, 0. And then you do minus the z derivative of f, but f only depends on x and t, so that just gives us 0 minus 0 for the I hat part of the cofactor expansion. Then you do the j hat part, but remember you have to alternate signs, plus, minus, plus. So then you have minus j hat times. And for the j hat part, we cross out this row and this column, and we have the x derivative of 0 and z derivative of 0. So again, it comes out a little bit boring, 0 minus 0. Now, hopefully, the last term, plus minus plus, would be plus k hat, will give us hopefully something interesting. And we do that, oh, we do see something interesting. We cross out this row and this column. We have the x derivative of f minus the y derivative of 0. So when we take the x derivative of f, we're just taking the derivative of f with respect to its insides. So that just gives me f prime of x minus vt, and then times the derivative of x with respect to itself, which is just 1. So writing this out carefully, then what we have is f prime, because we're doing the x derivative of f of x minus vt, times the derivative of the inside, which means partial of x minus vt with respect to x. That's the chain rule. And then minus, we're doing this k component, the y derivative of 0, which is, of course, just 0. And as we see, of course, this term is 0, this term is 0. We don't have to worry about that 0. When I take the x derivative of vt, that, of course, gives me 0 because there's no x there. So that gives me 0. And then partial x, of course, is just 1. So I'm left with f prime, derivative of f with respect to its argument of x minus vt in the k hat direction. That equals, this is the curl of v I've been computing, all of that equals minus the time derivative of the magnetic field, minus dB dt. All right. Whew. That was somewhat of a long calculation, but we've now are in a position to actually calculate the magnetic field. Let's think about what this is telling us. It sometimes is helpful, actually, for me to move this minus sign to the other side of the equation. So let's multiply both sides by minus 1, like so. And so we see we have a derivative, and we have to solve for the magnetic field B. And you all know the best way to solve a differential equation or to solve a derivative. You integrate, or in other words, you guess at the answer, and then you put in some constant of integration, and then you solve. So we have to figure out some function whose time derivative gives me back an f prime times this k hat. Well, remember, k hat is just a vector direction. It's just a constant, so we don't really have to worry about it so much. We can just carry it back down. And it looks like I want something whose derivative gives me f prime. Well, the best possible guess I could come up with for that would be just the function f itself. So let's let this be our guess and see how well we do. So I'm going to guess this is my magnetic field. Now, let's take the derivative and check. If I take the time derivative of this, I will get the derivative of f with respect to its insides. That means I'll get f prime of x minus vt. That's what I have here. Then I have to take the derivative of the inside with respect to time t, which is going to pull out a factor of minus v. And that's great, because I've got a minus sign here. But darn it, I don't want that extra factor of v. So what I'm going to do is I'm going to divide by it, so I'm not bothered by it in the future. And then, of course, k hat is just a constant, and that gives me my constant back again. So the derivative of this actually gives me my original equation back again. So this is my full solution for the magnetic field, except I'm missing one thing. There has to be some constant, but it's constant with respect to time, with respect to time t. To determine this constant, I, of course, can play the same game that I played before about infinities. Let's imagine that we are at time, say, t goes to minus infinity. Before I've even set up my apparatus, before I've done any experiment. Well, before I've done any experiment, of course, the magnetic field has to be 0. Nothing's happened yet. Now, for the magnetic field to be 0 as time goes to minus infinity, what I would get then is 0 for my magnetic field is going to equal 1 over v times my function f, my pulse. And when I stick t equals minus infinity in here, I'm going to get f at some very large value, right? Because I've got a minus times a minus infinity. So f at plus infinity, plus then again my constant. But f which is the shape of my pulse. I'm going to consider, some localized pulse like this. F at infinity is going to be 0. And so my constant has to equal 0. And because my constant is 0, I can actually eliminate this term in my integration. So here is just a little bubble, how we were thinking to determine the value of our constant. And this then is our result for the magnetic field. And so that is the consequence of Maxwell's equation number 3. And we now therefore have something that satisfies 2 of our Maxwell equations. So all we have left to do now is to check whether or not we satisfy the remaining 2 equations. Now I'd like you to notice something in terms of what we've learned so far about the electric and magnetic field before we check the remaining 2 equations. What I want you to look at is the following. If we look at our coordinate system, what we've been saying here now is we are having our pulse moving along x. That's the direction of propagation. The electric field actually is always pointing along the y direction. It, of course, may be varying in value, but it's always pointing along y. So if I sketch my little function f, my electric field vectors, right, they always point along the y direction. So here's my little pulse. Here might have a shape like this, right, as it's moving along. The magnetic field, as we've just derived it, points along k hat, or the z direction. And the interesting thing is that the magnetic field has exactly the same shape as the electric field, but it's pointing along z. So the magnetic field we've seen here, and it's reduced in magnitude by whatever this velocity is. So I'm just going to try to draw some magnetic fields. So this is what the magnetic field might be doing. So this is E in that direction and B in that direction. So we've just learned our next lesson. Lessons so far were that E was perpendicular to the direction of propagation. We've also just learned that B is perpendicular to the direction of propagation also, because it's in the z direction. But it's also perpendicular to the electric field. So you see that E and B form an orthogonal set of vectors that are both also orthogonal to the direction of propagation. So it seems that electric and magnetic fields set up and their direction of propagation set up some kind of a right-handed coordinate system. And the quick mnemonic for remembering this is, notice that if I say E cross B, that always gives me a vector that's perpendicular to E and B. And if I were to do that, because E is along Y and B is along Z, right-hand rule, fingers along E, curling up towards B, my thumb is to the right in the X direction, E cross B is in the direction of propagation. And the final rule that we've learned here is that the magnitude of the magnetic field is 1 over the velocity of this pulse times the magnitude of the electric field. So we have all of these nice relationships between the various directions and the magnitudes of the two fields, and all of these then have a special name. These are known as the polarization rules for the electromagnetic field. I'll leave you just with one final mnemonic, which is, how do we remember, is it E cross B or B cross E? Because the order matters to get the sign of the direction of propagation properly. And the answer to that is, just think about what we're talking about here. We're talking about electromagnetism. Electro comes first, E, magnetism, B comes second. So if it's electromagnetism, you should do E cross B, and that will give you the direction of the propagation of the energy, provided we can get the rest of Maxwell's equations to work out.